Hello Chem 1B, this is chapter 14, lecture video 8, and we're going to continue talking about how energy affects our rate constant. So last time we talked about how orientation and energy, you have to have both in order for a collision to result in a reaction. I always keep meaning to actually change this little phrase here because I think, peanut butter goes well with bananas too, so I don't know. You can't have one without the other, but this brings us to what we call the actual modeling of how temperature affects our rate constant. So the Arrhenius equation, this guy, is actually the equation that models how K is affected by temperature. And it involves really a bunch of variables, right? We have temperature, we have activation energy. This guy is what's known as the frequency factor. And we'll talk more about this on the next slide. But this is the molecular model for the rate constant, how it changes with temperature for any reaction. Doesn't matter what the reaction is, doesn't matter what the reaction order is. This is going to be the equation that we can use to determine K at different temperatures. So let's talk about this. K, that's the rate constant. A is what we call the frequency factor, or in other words, how often does our molecules collide with the correct orientation? So this is our kind of orientation component in this equation. EA is our activation energy, and that is the energy requirement. R is T is temperature. Now temperature, like with our gas laws that you learned about in Chem 1A, must be in Kelvin. Has to be in Kelvin units. If you use Celsius, you will get a wrong answer. And R, finally, is our gas constant. But it's not the typical gas constant that you might remember from Chem 1A. It's not 0.08206. It's another value that we did use in Chem 1A for the Clausius-Clapeyron equation. But it's 8.314. Now, the units of this R value are joules, moles, Kelvin, and you got to be very, very careful with that because activation energies are typically given in kilojoules per mole. Now, if you notice, kilojoules, I put that in red, kilojoules and joules are not the same unit. So since activation energies are typically given in kilojoules, you do definitely need to remember to change one of these values to the same units as the other. Now, generally, I just change this to joules per mole as my setup, but you do need to remember to do that. If you don't, you will get the answer wrong. It's kind of the most common mistake that I see with this equation. So what if we take the natural log of this equation, right? If we do that, we get a new equation. It looks like this, right? Natural log of our rate constant is equal to negative EA over RT plus ln of A. Now, you should be able to verify that on your own. But what's important about this is this equation, like other ones in this chapter, follows a similar setup as it's an equation of a line, right? So if we think about 1 over T, that's kind of like our X. Ln of A, that's our B. M, our slope, is really just equal to negative EA over R, and Y would be equal to ln of K. Now, we can graph 1 over T versus ln of K and get a line that should be straight with EA, negative EA over R as our slope, and ln of A as our y-intercept. Now, we can use the Arrhenius equation to calculate the activation energy, to calculate a rate constant at a different temperature, or also to calculate the frequency factor of our reaction. We can actually determine a second formula of the Arrhenius equation if I divide it by itself at two separate temperatures. And the equation I get is this. Now, I provide both of these equations on the test. You don't need to memorize them. You do need to know when and how to use them. But other than that, the equations will be given. You don't need to memorize them. So in this one, notice that ln of A is canceled out, and this equation is really useful when you have like a rate constant at two different temperatures and you want to solve for EA, or you have EA, a rate constant at one temperature, and want to solve for either the rate constant or the temperature of another setup, right? So again, I mentioned this earlier. What does this equation look like? It looks like a line, and we can graph it. ln of k versus 1 over t in Kelvin will give us a straight line with a negative slope, and that slope will be equal to negative EA over r, and our intercept will be equal to ln of a. Now we can use this to actually determine a lot of things, and we'll do that in the thermodynamics worksheet that's near the end of the semester. Yeah. And I think you have a couple problems like this in sapling learning as well, online homework. So again, if we wanted to solve for EA, that would just be equal to negative r times the slope of the line that we'd graph. So let's do a problem here, right? If the activation energy for a given first order reaction is this value here, let's use colors, this value here, with a frequency factor of this, we want to know what's the rate constant at this temperature. Well, since I was given the frequency factor, that's kind of like a clear giveaway that I'm going to be using ln of k is equal to negative EA over RT plus ln of A. Or you could use the other version of this equation. It doesn't really matter without the natural logs. But I can use all this. I know R is 8.314. I know I have temperature, which is 398 Celsius. I got to convert that to Kelvin before I do anything as far as plugging into the equation. But I can solve what I need to solve, right? So let's do some conversions, right? Let's find out what T is. Hopefully you guys remember that 398 Celsius, we got to add 273.15 Kelvin, or that to get Kelvin. So if we do that, we get 671 well, really we'll just leave it at 671 and leave out the 0.15. This is our temperature in Kelvin. Cool. So now we have this value. We already had R. There is another slight issue, right? Our R value is in joules, moles, K, and our activation energy is in kilojoules. So another thing I'm going to do is I'm going to take that 103 kilojoules per mole and convert that to just joules. This is just a metric prefix conversion, so you should have learned how to do this in Chem 1A. So we have this as our activation energy if I go from kilojoules to joules here. So next we just kind of can plug in, right? ln of k is going to be equal to negative 103,000 joules per mole, all over 8.314 joules over moles Kelvin times T, right, which is 671 Kelvin, plus ln of our A value, 4.00 times 10 to the 13 inverse seconds. And so that's my whole deal here. I can solve for this whole deal here and get a value. And what I get is that natural log of k is equal to 12.86. Now that's not k though, that's ln of k. So I need to take e of both sides here to get k. So k is going to be equal to 383,386, give or take. I mean, that's way too many sig figs, but I'm just going to kind of convert that to scientific notation, right? So that's 3.8, we'll just say 3 times 10 to the positive 1, 2, 3, 4, 5. And this is a first order reaction, so, and we used inverse seconds here for that, so this is just going to be equal to inverse seconds. And that's our answer. All right, so let's do another type of problem, right? So we have a data below, using the data below for this reaction, we have all that. And we want to know what is the activation energy for a reaction, for the reaction in kilojoules per mole, right? So in this case, we have one rate constant at one temperature, another rate constant at another temperature, and we can plug these guys in. We have the temperatures. We got to convert them to Kelvin, but then we can plug them in. and we have R. So we can solve this equation for the activation energy. Now, in order to do that, I'm just going to convert these to Kelvin right now, right? This is 298 Kelvin. This is 308 Kelvin. And it doesn't matter which one you call 1 or 2, right? Just as long as you're consistent, right? So I'm going to say, hey, ln of, we'll say this one's K2. So 1.48 times 10 to the negative 4 divided by 3.46 times 10 to the negative 5 is equal to EA, which is what I'm solving for, over 8.314 times 1 over T1 is 298 minus 1 over 308. And those are in Kelvin, right? So this whole thing, that was my equals sign, is totally solvable for EA at this point. We just need to do some algebra and solve. And this will give me an activation energy of about 110,000, give or take. I think there's a 9 here technically, actually. 0.5. And this is in joules per mole. It's joules, not the 5. Now, I would probably rewrite that in kilojoules, which would give me pretty much 11 kilojoules per mole as my answer. So let's do one more example problem. This is an iClicker problem, but again, we're not doing iClickers now that we're fully online. What is the rate constant at 80 degrees Celsius if the reaction has a rate constant at 25 degrees Celsius of this, and an activation energy of this? So again, we're using that same equation, right? ln of K2 over K1 is equal to EA over R times 1 over T1 minus 1 over T2. Right? So we have pretty much every value we need. I mean, I need to change this to 298 Kelvin and this to 353 Kelvin. But once I have that, I should also probably change this to joules, right? Which would be, 64,800 joules per mole. So at this point, I can go, hey, I want to solve for a rate constant. I'm going to make the unknown rate constant 2 because that keeps it in the numerator, which gives me one less step of work. So I'm going to say, hey, that's my unknown. And I have 3.25 times 10 to the negative 3 in inverse molarity, inverse seconds. And that's all equal to 64,800 joules per mole. Divided by 8.314 joules moles K, and then we do that times 298 Kelvin minus 1 over 353 Kelvin. And again, at this point, the first thing I would do is I would just solve for everything on this side of the equation and get a value. So let's do that. And what we get here is that natural log of K2 then over 3.25 times 10 to the negative 3 is equal to 4.075, give or take. This is a unitless value on the right because all of the units canceled, right? These kelvins canceled here, the moles canceled there, the joules canceled there. So now I just need to get rid of the natural log. So I'm going to take E of both sides, right? And what I'm going to get then is K2 over 3.25 times 10 to the negative 3, molarity inverse seconds inverse, is equal to about 58.86. Right, and the last step here, we just need to multiply by 3.25 times 10 to the negative 3 on both sides. And I'll get K2 is equal to, now the units also carry here, right? So whatever value I get, once I've multiplied these together, will have the exact same units as my other rate constant because this guy has no units. So once we multiply, we get the new rate constant is 1.91 times 10 to the negative 1 molarity inverse seconds inverse. And so here's our answer. Now it's bigger than the other one, which we should expect because we have it at a much higher temperature, right? 80 degrees versus 25. So we should have expected a bigger number. We got one, and that's good news. All right, so if you have any questions, please let me know. Discussion sessions or my email are the best way to contact me. Yeah, have a good day.